Hey, so this is the second problem set from my Organic Chemistry 1 class. And this is just the first problem set um, that we go over for the second unit. This basically just covers naming of alkenes and alkynes, um, reactions, either by knowing the reagents which cause these reactions or given reagents. You're you're to find what the product would look like. And also just knowing what reactions are named, um, and like given a scenario like this, we should be able to tell, like what process to use. Um, Small stuff like the Hammond postulate, knowing mechanisms for like simpler reactions because sometimes they get kind of hard. So at least in my class, I'm not really expected to know too much of the mechanism stuff. Um, and then also synthesis reactions, which is basically just knowing my reactions and knowing how to get to where I want. Kind of like solving a puzzle. So start with this first one. This is just naming for the IUPAC naming for compounds. So the rules for naming these alkynes is pretty similar to alkenes and alkanes, or just alkenes, where you want to number these so as to find the largest ring or chain containing the triple bond, and then number them so that the first triple bond is at the lowest number possible, and if they're the same, if you can start from either side, then go by the substituents. In this case, it's pretty easy because if you were to start from this direction, you get 1, 2, 3, 4, 5, 6. That doesn't really make any sense because then you have this cyclobutyl group that isn't really a part of the name, or you can't name it. It's weird. Or if you could take away the 6, then you'd have your first carbon triple bond at 5 or at 2, as opposed to if you did it this way, which is the correct way. You number it like this, so that your first carbon triple bond is actually on 1, and you have this cyclobutyl group hanging off. So the proper naming for this one is going to be, so we have the cyclobutyl, starts with a C, so that's going to come first, and nothing else. So we have 1 cyclobutyl, 1 comma 3, what is it? It is pentadiene. Easy. And this next one, find the longest chain containing the double bond, the alkene. And you also want the alkene to be at the lowest possible number when you're numbering the carbons. So start from this side. And then we'll have this ethyl group that's hanging off the side. So in this case, we'll have a 2 ethyl butane. Sorry, that's wrong. 2 ethyl, 1 butene, because this is this is an alkene, right? Same rules. Find the first or find the carbon chain or ring where the double bond is at the lowest possible carbon number. So we start from this side. It doesn't matter if we put this is 6 or this is 6. You'll still get the same thing. You'll get an ethyl group hanging off, or an ethyl group hanging off the 5. So in this one, we have at 2 we have the chlorine, and we have the chlorine at 2, and then we have the 5, which contains a methyl group. So chlorine will come first. So then the naming is 2 chloro, 5 methyl, 2, what is that? Hexene. All right, and then this one, you can try to number these. Any way like that, but it doesn't really matter because none of that actually contains the double bond that you need to name these in. And then for these, obviously you want to have it so that the numbering on the carbons makes it so that the double bond is at a lowest possible carbon number, and then after that go by substituents. So the best possible way to do this is 1, 2, 3, 4, 5. So this group is an isopropyl group, and then this one is just a methyl. Isopropyl is before in the alphabet. So the name is going to be 3-isopropyl, 4-methyl, what is this? 1-cyclopentene. All right, and then like for this one, we start with the first carbon on the very left because that's the one closest to the carbon double bond or the triple bond, the alkyne. Okay, so we do that, and then this would be a complex substituent on the bottom. So we want to number these again, 1, 2, 3. So that complex substituent is our only substituent, so we don't have to worry about the order. So we do want to start with 5, and then in parentheses 2-bromo propyl, because it's a 3-carbon chain. Close those parentheses, and then we have the triple bond at 1, and this is a 9-carbon chain, so this is going to be a non-ine. Hey, I wanted to make another note on this 1C part, that this is actually the E variant naming for this. Because there is some symmetry in here, you have to consider like the sides and which ones are more massive. And then you can say if the more massive parts of the double bond are on the same side, or if they're on opposite sides. And on this one, it turns out they're on opposite sides because if you consider on the right side of the of the double bond, you have a methyl group, which is, pretty small in comparison. It's going to be 12 molar mass for the carbon, and then 1 each for the hydrogen, so that's going to be around 15, and this chlorine is around 35, much more massive. And then on this group, or on this side of it, we have a carbon or a hydrogen that we didn't draw, and then we have this carbon up here and attached to everything else. So that carbon on top is going to be much bigger. So we have the big sides on opposite, are the biggest sides on the opposite side. So in that case, they are the E of that variant. And if they were on the same side, like instead of the biggest groups were here and here, it would be Z, but it's not Z, so yeah. Okay, so in this second question, in each synthesis, either the reagents or products are missing. Fill in the major reagents or product. If there's more than one product, show only the major one. Show stereochemistry where appropriate. So the only thing that's changing between the reactants and the products is that we have lost the halogen, the chlorine, and we're gaining a double bond there. So this is the process of dehydrohalogenation. And that it does exactly that. It replaces the site of a double bond, or the site of a halogen with a double bond. And we'll go over some of the mechanisms or the things that actually happen in these reactions later on, but in this one we'll just fill out the actual the reagents or the products. So the reagents that you use for dehydrohalogenation are going to be, or at least the ones I've learned, I'm sure there are others, but and I learned these as to remember them as cock. Yeah, and then that's pretty much it. So this one, this is going to be the process of alkylation. It looks very similar to the process of preparation, but in this case we have a second step, which is adding to the end of it that this whole group thing here. You lose the halogen in the process and you just get whatever this is. So the end product, or the major product, is going to be what we have here, this benzene. It's like that. Oh no. Something like this. All right, pretend that's a benzene. That 6 carbon ring, and then we have what we have originally, but we also have attached to it. Oh, my drawing's horrible. Then we have something like that. So it's basically going to be replacing just the hydrogen that's like imaginarily here with whatever this thing is in the second step. I might show the mechanism later. I don't remember. Okay, so that's that. And then this is going to be halohydrogen formation. You can remember it just because you have a halogen and a water, the hydro part of that. And the reactants are just going to be those, and then the solvent that you're going to be doing this in, I guess, is this dimethyl sulfoxide solution. And this is going to be, you lose that double bond on the end there. You have that. You have some OH out there, and then you have the Br group. I think I explained this later, but this OH group, this OH group right here goes into the more substituted carbon, because whenever you're forming bonds, you form a slight positive charge on this carbon right here, and whenever that basically becomes a carbocation, and from the carbocation rules, we know that a more substituted carbocation is more stable. So adding this alcohol group on that makes it more stable. So yeah. And I guess for this one I don't really have to show it, but there's some hydrogen or whatever. So this process is going to be for question D. The only thing that's different between the products and the reactants, is that we lose this double bond, and this is called hydrogenation. It makes sense because both of the carbons in the CC double bond only have one hydrogen on each one of them, and then after they each have 2 on them. So it's kind of like, the name makes sense. You're just saturating those 2 carbons with more hydrogens, and the 2 reagents in this are going to be H2 on a palladium, or with palladium on a carbon surface. So yeah. And then this next one, what's happening is that we're getting rid of this alkyne, this triple bond, and we're not reducing our bond order all the way down to just a single bond. We're just going from a triple bond to a double bond. So in this case, we want to use hydroboration, I think is what it's called. So you get this BH3.THF for our reagents for our first step, and their second step is going to be this peroxide, and then sodium hydroxide. So yeah. On to question 3. A reaction occurs in 2 steps. Both steps are exothermic, and the second step is rate determining step. Draw an energy diagram showing energy versus reaction coordinate. Label the reactants, products, intermediates, and transition states. According to the Hammond postulate, will the second transition state resemble the intermediates or the products? Okay, so we know both steps are exothermic. Forgot what that was for a second. All right, so we know the reactants are going to be higher energy than the products, and we just kind of just draw this to scale. Something like this. Okay, that looks pretty bad, I'm not going to lie, but We'll say these are the intermediates because that's like the plateau in this curve. This is going to be TS1, transition state 1, and then transition state 2. Reactants over here, products, and then both of these reactions are exothermic in nature, or both steps of it. And we're looking at transition state 2 up here. And then according to the Hammond postulate, the transition state will look more so like the closest step in the energy diagram, or it'll look more so like the chemicals or the substances that are closer in energy to the transition state. So we can see this is like the height from the transition state, and then this is the height from the products, so it's closer to the intermediates. So therefore, transition state 2 looks closer to intermediates. Question 4, show the mechanism of the reaction below. It may help if you have just a certain types of reactions memorized to know that this is just halogen addition or addition of halogens, whatever. I'm just gonna work on the side just so we have more space. So basically we start with this wow, that's pretty bad. Draw the inside. We start out with this pentene ring, whatever. And our next step is going to look something like this Br plus. And that basically happens because when this bromine gas from over here kind of comes close to this, we know that these double bonds aren't the most stable, so they will react with things that are also reactive. So this double bond is kind of going to attack this bromine, try to attach to it, and the electrons in this bond will go to this bromine to make that into a negative one. And this is where you form this bromonium ion because the bonds kind of don't know which one to attach to. And that's also very unstable because they don't have their own things. It's kind of like an intermediate. So that's where this other bromine, the one that got torn off, this negative sign bromine, this its electrons attack this this carbon right there, and then the electrons in this bond go to this other carbon, and then you are left with this bromine on either side of where the double bond used to be. And you do have to show that these were I guess one is into the page and one is out of the page. Just because if you want to think about like a side view of this thing, the bromonium ion is actually kind of like this. It's kind of like both up. And this reaction is almost like sterically controlled because there's a lot of space on this bottom region where nothing is bonded. So this other bromine, the bromine minus, it'll come up here and try to attack one of these so that now one of these bonds will be upwards, the out of the page ones, I guess, and then this other one will be into the page. So yeah. Question 5, the reaction below is called the Pinnacle rearrangement. Show the mechanism of the reaction. This isn't one we did in class, or we did in my class, but my professor said it was fair game because all the steps are stuff that we've done before. So, yeah, we'll start. So we start, forgive me, I'll just rewrite everything. Okay, so the first step is this H2SO4. It dissociates a little bit because sulfuric acid. It's an acid. You have some H plus or some H3O plus floating around. So we have some H plus, kind of that attaches to this this alcohol or this OH group. So then you are left with pretty much the same thing, but that on this we'll have O, and then kind of a structure like this where the positive charge is on the oxygen, positive formal charge. And then the next step is kind of easy. I'm sure this looks similar. It's just water, so it basically just rips away from the atom, takes some of the electrons from this bond, and then you are kind of left with a hole in the structure and a positive carbocation right there. And then at this point, one of these methyl groups, these CH3s on the end here, will actually kind of like shift over here in what's called an alkyl shift, just because we remember that as it stands now, we kind of just have these two methyl groups and then connected to another carbon, which isn't really anything. It's pretty stable, but it can be more stable. So whenever we actually shift this methyl group over, the carbocation will shift to the left, and you'll be left with something that resembles this. Yeah. So you'll kind of be left with this. And if you notice, it looks kind of similar to what we had in the last step. But this makes more sense because alcohol is a bigger group. It has a higher electron density, so it can more so stabilize that positive charge in the carbon. And then after this point, oxygen has 2 lone pairs over here. Oops. So it can donate one of these lone pairs to the carbon over there, and then you're just left with H3C. And then you're left with OH minus. Oops. CH3. And then we still have the negative charge on this on this OH group. My bad. This positive charge. So then one of the other molecules of these of the pinnacle will take away one of these hydrogens, and it'll keep continuing the reaction. So this will go out, and then you're just left with your final product of H3C. And yeah, and once this oxygen is left alone, it'll form a double bond. Well, that doesn't really make any sense. I'll have to come back to that. And then for this last problem, number 6, planned synthesis or planned syntheses of the following compounds. You may use the given starting material and any compound containing 3 or fewer carbons. That pretty much aligns with anything we've used from this class, just because none of it really contains that many carbons. I don't think so. Okay, so, and for this we don't have to show mechanisms, so we can just show exactly what happens whenever I use whatever reagent. So I'm sure you guys know synthesis, or maybe not. Synthesis, I guess, like notation is like backwards. This is what we start with, and this is what we end up with. So this looks like, this right here looks like the problem we did earlier, where we just did bromine, or halogen addition or halogenation, whatever you want to call it, to a pentane or cyclopentane. But when we did that, we had a double bond to start with, and this we don't. We need to make one. So I'm just gonna go to the left of these. So we start out with this Br, and then we want to use the thing I talked about earlier, I guess, the cock. And what this is going to do, these will aid in the process of dehydrohalogenation, where we're going to take away the halogen and take away some hydrogens in the process of creating the double bond, unsaturating those carbons. And then we'll be left with this double bond, cyclopentene. And then as a last step, we'll just use Br2, and it'll be pretty similar, with the whole thing creating the bromonium ion and whatever. And then we'll create this. And yeah, it's a little bit of a different orientation. Make sure to show that these things are into the page, not at the page. It's different orientation from this, but just flip it around. It's the same thing. And then for this next one, we have a benzene, or cyclohexane, with a methyl group and then an alcohol group. Well, that's what we want, but we have it so that the methyl group and the alcohol group are on the same corner. We don't want that. So basically, given this, we need to find a way to move the alcohol around, or the OH, and we can just leave the methyl group there. Don't need to do anything with it. We might have to move it in the process, maybe not. So for removing the OH groups, this is called dehydration. This is just going to be using an acid and THF for the solvent, or the organic solvent. And then we will be left with that cyclohexane. I drew that sideways. I wanted to, my bad. We'll have the double bond there and still have that methyl group hanging off the side. And then to get the hydroxide back on that bottom right-ish corner, we want to use what is it called? Hydroboration, because if you were to use oxymercuration to rehydrate, that the oxymercuration follows the Markovnikov rule, so that the OH group will land on the more substituted carbon, which would be this one, and that would just give us the same thing we started with. But if we use hydroboration with the reactants or the reagents BH3.THF and then this peroxide NaOH, If we do that, the OH will be on the less substituted carbons, so then we'll be left with methyl group and then OH. So this one confused me whenever I was first doing it because I thought this was just like a poorly printed line, but that's an iodine. So this is basically just getting rid of the halogen there, and we can do this in 2 steps. So our first step is to, sorry, that's cramped. So we have that iodine there, and then we want to start with dehydrohalogenation. These are going to be the same reactants as over here. The Cock. That's how I remember them. Maybe it'll help you. So then we'll be left with and then I accidentally used a bit too much space. And then to bring that bond order down, or to make that double bond single bond, and to not have anything attached to it or anything weird, we're going to use hydrogenation, which makes sense. We're just adding more hydrogens to these carbons, saturating them. And we'll do this with our reagents of hydrogen gas with the palladium on carbon. And then we'll be left with the thing we want. And it's also important to remember that whenever you're, I guess, choosing where this double bond is going to be placed, what was it? I think it's Zaitsev's rule. And you gotta, like, I guess, consult alkene stability. The double bond is more stable because double bonds are inherently less stable. So the double bond will be in a more stable state or position whenever it's on or connected to the more substituted carbon. So, like, let's say if we were to draw it here, each carbon on the corner would only have like one thing connected to it. So yeah. And then because the double bond is drawn here, we have this carbon here, which has 2 carbons connected to it, and this one only has 1. So that's better than both of the carbons on the double bond only having no substituted things, or 1 or none. Okay. So for our next one, we basically just want to, I guess, hydrate that in the middle position. Okay. All right. So we start with our starting molecule. We want to take off that halogen and make it a double bond. Yeah, we want to make that a double bond. And then we will be left with something like that. That's the only possible place for the double bond, so there's no question of anything. And then, and remember, again, this process is dehydrohalogenation. And then that kind of seems like counterintuitive because we only wanted to add the hydroxide, but we don't have the hydroxide and we took off the halogen, the bromine. But then we can use the process of halohydrin formation, just like how it sounds. We're adding halogens and hydrogens there. So then we'll be left with Br, and then OH. Yeah, and basically the hydroxide is going to be on this carbon here, because it kind of goes over. I forgot what it was. It was. I think it was like carbocation stability whenever you're forming these. I think that carbocation, or this kind of becomes a partial carbocation over here, and adding the hydroxide or this OH group is more stable. It has more functional groups attached to it. And then for this last one, this part E, we want to take that double bond, or that whole double bond thing, that ethene, and just replace it with a bunch of chlorines. So I think this one is actually like a 4-step process or 3-step. It'll be one more than the other ones we had. There'll be 4 unique states. So we start off with this benzene. Start off with that. And then we use bromine or some other halogen for halogenation or halogen addition, whatever. And then we'll be left with that same benzene ring, but instead of a double bond, we'll have 2 bromines or whatever other halogens. And then the next step is we want to do preparation and use this super strong base over here. Just do a plus. And what this will basically do, it'll basically react with the HBRs or the hydrogens and the bromines on each one of these on each one of the carbons. And then you'll be left with just one hydrogen, and in that arrangement, the only thing that can exist is another triple bond that you're making. So then you end up with the triple bond, which is like that, and then you have this, and then you do alkylation to basically break that triple bond down again and replace everything with just chlorines. So then we'll use NaNH2, NH3, and then Cl2 for our halogen this time. We could have used it for the first step, but just chose something else. And then we'll be left with this benzene ring. Yeah, that's everything. Clarification for 1D. The reason why this OH shows up here on the more substituted carbon rather than this outsider part is because so the first thing that actually reacts with that double bond is going to be the bromine, and it's going to form a similar or it is going to form the bromonium ion, where there's going to be a bromine with like having 2 bonds connected to it. And then this OH is going to come out of here from nowhere and try to bond with this carbon. So the electrons from the bond on this side will flow to this bromine to make it electrically neutral. And this will form like a carbocation, like a partial carbocation. And from our carbocation stability rules, we know that a more substituted carbocation is more stable. So this hydroxide will attach to this carbon because it is partially positive, and it needs to accept those electrons from this OH group to be more stable. So yeah.